A warm welcome to you all to the next session on electronic devices. So, till the previous session we completed module 2 and we understood what is a PN junction device, how does it work, and then also we understood this PN junction is called by a name which is called as a diode. We understood the working principles in the forward bias condition, reverse bias condition, and we have also seen the applications of this PN junction diode. That is the solar cells, the photodetectors, and also which is the LEDs, that is light emitting diodes. Now starting from today we will be commencing module 3, that is about BJTs. So what is this BJTs? It is bipolar junction transistors. Now, why do you have to study this module? What all you will be understanding in this module? So, the scope of this module is, this module will help you to gain the strong understanding on a device which is called as a BJT. And this is one of the semiconductor devices that can be extensively seen in many kinds of analog circuits that will be coming across in the upcoming semesters. So it is very much important for you to know how does this BJTs work and what is the main reason for using the BJTs in any kinds of circuits that you will be considering. So that is the reason why you need to understand this module. That is where the importance of this module comes into picture. Now, what all you will be understanding in this module is, as I mentioned, it is that you will be understanding how does this BJT is being constructed, followed by what is the working principle of this BJTs. Now, when I say working principle, we will be almost importantly considering about the carriers which is being injected or how does the current flow happens in the BJTs. Now, once we are done with that, we will be looking into the different regions of operations related to the BJT and followed by the applications of BJT. We will also be looking into how these BJTs are being fabricated, how it is being manufactured. So that also will be looking into. So these are all the glimpses related to the topics that will be covered under BJTs. Now, why it is called as bipolar junction transistors, we'll understand that a little while later in the same session. Before going into that, now let me just have a quick revision regarding the topics that we have considered priorly that will relate to the BJTs, which we'll get to know a little while later. Yeah. So, the very first topic in the BJT module is 3.1, which speaks about the overview of BJT operation. Now, in this particular topic, we'll try to gain some physical understanding on how the charge carriers are being transported in a BJT device. Yeah. Now, before going into that, before going into the depth of the BJT operation and construction, let me just consider a PN device. Let this PN device be uniformly doped, and then we know there is a certain depletion region that can be absorbed, and let me consider this particular PN junction device to be connected in the reverse biased condition. Now, when I consider a reversed biased PN junction, we know that in this reversed biased PN junction, what is happening? The minority charge carriers, that is the holes which is present in the N type, gets swept to that of the P type because of the electric field that is present, and this has nothing to do with how much amount of reverse voltage that I am providing. We have seen that it is all about whatever the reverse current that is flowing in the reverse bias is all about how often the holes which is present in the n-type get swept through the p-type. It is not about how many of them are getting moved into the p-type material. So this has nothing to do with the strength of the electric field that is present in the junction that we have seen in the previous session, right? So while starting off with the module 2, you have understood this concept in the very first topic of module 2, that is whatever the reverse saturation current that is flowing in the device has nothing to do with the intensity of the electric field that is present in the junction. And this shows clearly that it is independent of the amount of reverse voltage that I am providing. But what it is in turn dependent on? It is in turn dependent on how often the holes which is present in the n-type get swept to the p-type, and how often the minority carriers, that is the electrons which is present in the p-type, get swept to the n-type. Right? Now, what does this define? How do you define this factor? See, more the number of minority carriers being present in the n-type, more often the holes get swept to the p-type material. More the amount of electrons that is present in the p-type, it is being generated, more often these electrons get swept to the n-type, which in turn will increase the amount of reverse current that is flowing in the device. Right? Now, how does these carriers can be generated in the n-type and p-type so that I can increase the reverse current? Now, one of the factor or one of the methodology that we have seen in the previous session is that I'll be making a light of certain intensity to fall on this p-n junction device, and the energy of this photon is greater than that of the semiconductor band gap. Now, when this happens, this will in turn generate the EHP pairs in the N, P and this in this region, which in turn will increase the amount of charge carriers that is being swept to the p-type and the n-type materials. As a result, it in turn will increase the reverse current that is flowing in the device. Now, if I want to represent that in the graphical form, if I want to plot that, now before this optical generation part, whatever the reverse current that was flowing in the reverse bias, what is that being referred as? Dark current. Yeah, and this dark current is purely a function of the thermally generated. It is a purely function of thermal generation. Now, what is this current referred as? It is called as dark current. Now, as I tend to provide certain light energy, what is happening? As I tend to increase the amount of optical light that is being incident, the reverse current also tends to increase, which in turn will indicate whatever the generation of the charge carriers, that is the EHP pairs that I am doing, optically as it tends to increase, the reverse current also tends to increase. Done? Now, one key point you need to know here is, if in case this thermally generated current, which is the dark current, is minimal, then whatever the current that is flowing in the device is completely or it is directly proportional to the optical generation rate. And we have already seen all these factors. Now, why am I saying all these factors is, now this will rise to an important and an interesting question. Now, what is that question is, if in case I can find an alternative method that will help you to inject the minority carriers. See, because of the incidence of light, we are trying to generate the EHP pairs, right? Now, what are those EHPs? These are nothing but the minority carriers. Now, instead of optically generating those EHP pairs, if in case I can inject these minority carriers to this N region, say for example, if I can inject the minority carriers holes to this N region, more number of charge carriers if I can inject, more will be the sweeping of the charge carriers and more will be the reverse current. So, can I provide such an alternative solution instead of having the optical generation? Now, let's try to see and understand this scenario by considering a figure. Now, what I'll try to do is, I have the same PN device which is being reverse biased, and there is a load that is being connected. Let me just represent the supply as E. Done. Now, what is that I am trying to do? I am trying to have a whole injector. Let me just represent the whole injector like this. Now, what will this whole injector do? This whole injector will inject the minority carrier, that is holes, into the N region. And then once it is injected, because of the electric field that is being present, it gets swept to the P side, which in turn will increase the amount of reverse current that is flowing in the particular circuit. Done. Now tell me, will the rate at which these holes are getting injected, will it define the amount of reverse current that is flowing in the device? Yes, because we know that it is all about how often the holes are getting injected into the P-type material. How often it is getting swept to the P-type material. So more the holes that I inject, more often the holes that I inject into the N-type, more often the sweeping process takes place, then more the increase in the current can be observed. Right. So, this is the principle or a second alternative solution that I can have instead of doing it through optically excitation. Done. Now, if in case I can have a PN junction that will in turn helps to provide this, or that will in turn will do this whole injection, then such device can I connect it with this and then see how it works basically. So, whatever the whole injector that I have considered here, if in case, how is that basically happening is, if in case I have a device which is having a P plus N region, we know the depletion width here is small and here it is large because this is heavily doped and this is lightly doped. Now, if in case I have such a configuration which is basically forward biased, now what is happening here? Since the P plus is heavily doped, it has more number of holes. That holes, when it is in the forward bias condition, what is happening? These holes are getting moved into the N-type region, that we know, right? So, because whatever the depletion width that I am observing in the forward bias condition is narrowed down, whatever the electric field intensity that I observe in the forward bias condition is narrowed down. As a result, more amount of charge carriers can get diffused into the other region, and also in addition to that, this is heavily doped. As a result, more amount of holes that is present in the P-type can be injected into the N-type. Do you agree with me? Now, is there the whole injection that is happening from the P plus region to that of the N region? Yes, that is happening. Now, relate this with that of this particular circuit and see if I can have this N region as same as common as that of this N region. That means, if I can have a P plus N region in common followed by a P region, wherein this P plus N region will act as a hole injector which will inject the holes into the N-type, that is the minority carriers, that becomes the minority carriers in the N, which in turn will reach into the P. That is how I can increase the reverse current that is flowing in the device. And that resultant semiconductor device that I will be getting is what is referred as P plus N is common followed by P, that is P plus NP semiconductor device. Done. Now let's try to write this diagram and see what are the constructional details and what are the different kinds of charge carriers that flow in this device and how will I represent its characteristics. Okay. Now, what is that I am trying to do? I have a P plus region and then I have an N region. And how are these connected? They are in the forward biased condition. Done? Now, I have to have another region which is N and P. So, I'll have an N region which is common and then I'll have a P region. Now, how are these N and P regions are being connected? They are connected in the reversed biased condition and we have a load with it. So, let me just represent this to be as RL. Done? Now, what happens to the depletion width that I have? Here it will be less wider, whereas here at this end it will be widened little more. Then since these are lightly doped that I have been representing, let me just show the width to be increased. Done? Now, we have many factors to understand in this particular configuration. Let's try to go one by one. Okay? Now, so there is an N region in common between the P plus and the P region. Now, how is this particular junction? This P plus N junction is being forward biased and this N and P junction whatever we have is reverse biased. Yeah. Now, whatever the two junctions that I have, since I have two junctions, then there are four possible configurations that can arise. So, what are the four different configurations is, either I can have both of them to be in the forward bias condition, either I can have this to be in forward bias and this to be in reverse bias as I can see right now, or I can have this to be in the reverse bias and this to be in the forward bias condition, or I can have both of these to be in the reverse bias condition. And these four different configurations will define the four different regions of operations when I consider the BJT. Done? As of now, we are only interested in, we are looking into the one of the modes of operations, that is this junction is being forward biased and this junction is being reverse biased. Now, since this particular region, that is the P plus region, is the one which is helping you to inject the holes, I'll represent this particular region, or I'll be the one which will, I'll mention this region to be as emitter region. Now, why am I calling this as emitter? Because this is the region which is emitting the holes into the N type followed by to that of the P type. Getting my point? And therefore, I represent this particular region to be as emitter region. Now, whatever the holes that is getting injected into the N type will be reaching the P type because of the reverse bias junction that I have, that drifting takes place. Now, since this P region is collecting majority of the holes that is being injected by this P type, P plus type, what will I represent this terminal or this layer of the PN junction to be as collector, since it is collecting the injected holes from the P plus region. And whatever the region that I have right here is represented as the base region. Therefore, whatever the BJT that I am considering, it is how many layered semiconductor device? It is a 3-layered semiconductor device. Now, what are these 3 layers referred as? Emitter, base and collector. Done? Now, do we have 2 junctions here? Now, how do I call these 2 junctions as? Now, whatever the junction that I have here, since it is a forward biased junction and it is near to that of the emitter junction, this is the region where, or this is the junction where the holes are getting injected into the N type, and this junction I'll call it as emitter junction. And this is the reverse bias junction where the holes are getting diffused and getting collected by the P region. Therefore, I can consider this particular junction that I have as collector junction. Done. Now what are these two junctions referred as? Emitter junction and collector junction. Now tell me, how is this emitter junction? In which mode it is? Is it in the forward biased or reverse biased? It is in the forward biased condition, whereas this collector junction right now, according to the batteries that I have connected, this is in the reversed biased condition. Done till here? Yeah. Now what are the three different terminals that I have? Let me represent this P plus near to the P plus as emitter, which is represented by short form as E, and this as base, which is to that of the common N-type material, and this node to be as a collector, which is near to that of this collector P semiconductor region. Now, whatever the holes that we have in the P plus region, I want all the holes which is there in the P plus have to be successfully injected into the P type material. Now when this injection of the holes is taking place, when this is happening, now that holes have to pass through this N and then followed by the P region. Now when these holes arrive at the N region, what do we have in the N type? It is the electrons that we have, right? Now is it possible for there is a recombination that takes place, because we have a hole as well as an electron. Now can they recombine? Yes, it is definitely possible. So if that happens, the amount of holes gets reduced which is getting injected into the P type. Now, is it a good phenomenon that takes place? No, it is not. I want as much amount of holes that was there in the P plus have to reach to the P type. That means I need to reduce the amount of recombination that is taking place in the N region. Now, how can I reduce the recombination that takes place in the N region? Is all by making the width of this N region to be as small as possible. And also I'll ensure this N region to be of lightly doped. As a result, we can have fewer electrons that can recombine with the hole, and majority of the holes that can then get transferred or get injected into the P type material. Done. Now what is the condition you have to remember? This N type have to be lightly doped and the width of this base region should be as narrow as possible. Now when I make this happen, what is the result that I'll be getting? Majority of the holes which is there in the P plus gets injected into the P region, that is into the collector region. Now let me just represent this width of the base region, starting from this depletion region at the emitter to that of the depletion region to the collector. That is where the width of the base comes into picture. You cannot take it out inclusive of this depletion regions. Please note that point. And let me represent this width of the base region to be as WP. Now what is the condition that you have to follow is the width of the base region have to be very much smaller than that of the diffusion length of the holes. Now what does this LP indicates? It is the diffusion length of the holes that takes place within the N region. Now if the holes can get diffused into whatever the length of diffusion that takes place, if it is very much greater than that of the width, then it can easily penetrate into the P-type material. That is what this basic condition indicates, where the LP is given by root of dP into tau P. Now, what does this tau P is? We know that it is the average lifetime of the holes in the N-type material. So, how much time or for how long the holes which is present in the N-type will be alive, that is before going into the recombination, how long it will be alive. So, more the amount of average lifetime of the holes, more it can diffuse into the P-type without getting recombined with the electrons, and that is what I am looking into. What are the conditions? The diffusion length should be greater, the average lifetime of the holes should be greater. So, compared to that of what? That is the width of the base region. So this is one condition that you need to understand. Done? Now, how is the movement of the holes is happening here from the P plus to to that of N to that of P, and then it has to go. So if it has to start from the P plus, then from where it has to start? From this region it has to start, right? Therefore, this whatever the current, I'll be representing as the emitter current, and then whatever the holes that we have, it has to somehow get injected and then come out like this, right? Therefore, it is coming out of the collector region. As a result, I represent the arrow direction to be in the outward direction when compared to that of the collector region. So this is the incoming current and this is the IC is the outgoing current. Now we have one more current at the N region, intermediate N region that I have, and this current is what we call as base current. Now what contributes to this base current is what we'll try to understand now. Done? Now please be careful with this, because there are many things that is happening within this P plus N and P region, because we have majority carriers as well as the minority carriers which is playing its role. Yeah, so you need to understand all these factors. Therefore, let me try to take up a circuit or a P plus NP region which will clearly define what are the different kinds of currents that you can observe in this particular structure. As I mentioned, there is certain amount of current that also flows in the base region, right? Now, why does that current flow basically happens is, there are three different conditions that you have to understand, which in turn will result in the base current, which in turn will impact the base current that is flowing in the device. Even though there should not be any amount of base current, I want the emitter current should be exactly equal to that of the IC. But still there exists certain base current, and now I am trying to understand what are the three different causes or the reasons that will result in the base current. Now the first and the foremost reason here is, see, as I told, whatever the P plus region that I have, the holes that is present in the P plus, since it is forward bias, this emitter junction is forward bias, these holes gets injected into the N-type material. Now all the holes which gets injected into the N-type, the majority of them gets moved into the P-type because of the reverse biased collector junction that I have, and few of them will undergo the recombination. However, I try to make this width to be small. I try to maintain that condition. What is that? WPB should be as less than that of the diffusion length of the holes. Still there is certain amount of recombination that takes place. Now when this recombination takes place, then there is a reduction in the electron amount that is present in the N-type that needs to be compensated, right? Now how will I compensate that? Is by providing the electrons through the external source that I have connected. These is the external sources that I have. So these external sources, what will it tend to do? It will try to provide certain electrons into the N region. Why? Because we need to compensate the electrons which is recombined with the holes that is coming from the P plus region. Now once these external sources are providing the electrons to the N region. How does the electron flow happens? That is in this direction, that is towards the N, right? So if that is the case, then how will I represent the current? Should be in the reversed direction, because we are representing the conventional current. Therefore, how will I represent the base current that is flowing? It should be in the outward direction. Now that is regarding the first reason. Because of the recombination that takes place in N, it has to be compensated. Those number of electrons needs to be compensated, which will be provided by the external circuit. Since the electrons are provided in this direction, the conventional current have to be in the opposite direction. That is regarding the first case. Now coming to the second reason. The second reason is whatever the electrons that is present in the N will also tend to move into the P plus region. Right? Now when these electrons tends to move into the P plus and then recombine, whatever the electrons that we have lost here have to be again compensated by the external sources. So inclusive of the recombination and the electrons which is moving into the P plus, both of them have to be compensated. Now how that can be compensated? It is because of the external sources which is providing the electrons. Done? Understood with the first two reasons. Now let's try to look into the third reason which make this particular base current to be in smaller in quantity. Now what is that is, whatever this P region that I have, this P region also contains certain amount of electrons which is the minimal or the minority charge carriers. Right? Now whatever the minority charge carriers that I have, if in case they can diffuse and get into the N region, what happens to the number of electrons that is present in the N? It is trying to increase, which in turn will help for the compensation that I am trying to do because of the first two reasons. As a result, what happens to the IB current that I can see in the device? It will be reduced. Done. So the three key points, the first is the recombination, the second is the holes that is getting diffused from the N type to that of the P plus. Both of these needs to be compensated. For that reason, externally you are trying to provide the electrons, therefore the conventional current direction have to be reversed. And then there is also certain electrons which is present in the P type is trying to move into the N type, which in turn will increase the carriers, that is the electrons in the N, which results in the reduction in the IB current that I can see. So these are the three reasons that will result in an IB current, and this IB current is usually seen in terms of microamperes, whereas the emitter current and the base current that I can observe, it will be in terms of milliamps. Therefore these two will be in terms of higher value when compared to that of IB. Now what about the doping? This has to be heavily doped, these have to be lightly doped. What about the width? This have to be very narrow down, whereas this can be of a little larger. Done till here? All of you understood with this? Now let's try to look into the different current components that I can see in this P plus NP semiconductor device, that is a BJT device. Now there are different arrows that you can see in this diagram, right? So there is nothing to get panic. It is a very easy concept. Let me just make you to understand that. See, the electrons are flowing from the emitter to that of collector, and majority of the holes which is present in the P plus is trying to reach the P region. As a result, I have kept this arrow to be bigger in size. Done. Now see, this arrow is maintained till this point, and afterwards there is a little reduction in the arrow size. Now why there is a reduction in the arrow size? When I compare this width and this width, when I compare, there is a reduction in the arrow size. Why? Because there are certain holes that gets recombined with the electrons which is present in the N type. Yeah, and that is what this first factor indicates. Now, after recombination, whatever the left ones that we have, it will try to cross this reverse biased collector junction and move into the collector region, and that is what the current which results in the second component. I hope all of you understood with how should be the arrow size till this point and why it is reduced after this point. Done? Now, there is certain amount of electrons which is provided from the external source, because it has to compensate with the electrons which we have lost in the N material because of the recombination, moving of electrons from N to P plus. So that electron flow is what I am trying to show here from the external circuit, and out of these electrons that I am receiving, few of the electrons will come into the N region, which results to the fourth component of the current, and few of these electrons again tries to get diffused into the P plus region because it is forward biased. This junction is forward biased, and that diffusion current that I can see, that current I can see is what being represented as a fifth component in the current. Done. Now what about the third component that I have is, even though this is reversed biased, the minority carriers which is present in the p type, that is electrons, will try to get moved into or drifted to the N region. That is what this arrow indicates. And also the minority carriers, that is holes which is present here, will get drifted into the P region. That is whatever the holes that I have received from here to here and then from here to here. So that is what this arrow indicates. And these two totally represents the third component of the current. Therefore, totally how many current components I can have? 1, 2, 3, 4 and 5 current components, and this will indicate the basic operation of the BJTs. Done. Now let me tell you why it is called as a bipolar junction transistor. Now as you can see, what does bi indicates? 2. What does polarity indicates? Positive and negative, two polarities. What are the two polarities that I am referring to in the P plus N and P regions? The holes which is positively charged and the electrons which is negatively charged. That means to say, both the holes and the electrons which is present in the BJT will help for the current conduction. Got the point? And then why there is a junction here is, we have two junctions that is being formed because of the P plus N and P regions. What are these junctions referred as? Forward biased emitter junction in this case, and this is the reverse biased collector junction for this particular connection that I have provided. Therefore the name junction. And what is a transistor? That is a kind of device that I get because of the P plus N and P regions, and that's why we name this kind of a device as a BJT. Now, is this the only configuration that is possible? No, there are two basic configurations, and those basic configurations are PNP BJT transistor and the other one is NPN. Done. Always remember, in any of these the emitter have to be heavily doped, these two have to be lightly doped. The width of the base should be as narrow as possible. Done. And then these are the two different configurations of BJT. Now let me try to see if in case the emitter junction and collector junction, what are the four different cases that I mentioned? Forward biasing and reverse biasing. Let me just tabulate that and tell you what are the different regions of operation. We'll just go into that in details in the upcoming sessions. So this is the emitter junction and this is the collector junction that I'll represent, and let me just say the mode of operation. Now what are the four possible cases? I can have both of them to be forward biased, emitter junction to be forward biased and collector to be reverse biased. Then this to be reverse biased and this to be forward biased, and both of them to be reverse biased. Now if in case both the junctions are forward biased, then this is the mode of operation is referred as saturation region of operation. If in case I have both of them to be reverse biased, then that mode of operation is called as cutoff region. And right now whatever we have considered, that is the emitter junction forward bias and the collector junction reverse bias, this is referred as forward active region, or simply in most of the textbooks they'll refer just as active region. Done. And then comes the reverse biased emitter junction and forward biased collector junction, which is referred as reverse active region which we are least interested of. So this is the region where we will make the device not to operate. So if I am operating the device in this region, then what is happening? There is an amplification of the current that takes place, that is in the active region. Whereas if I make the device to operate in the saturation and in the cutoff region, this is the regions where my device, that is the BJT, will operate as a switch, will operate like a switch. So that is where the two kinds of applications of BJTs comes into picture. One is to perform amplification of the current signal, whereas the second is to perform as a switching operation. And if in case I want to make them to operate in switching mode, these are the two regions. If it is for the amplification purpose, this is the region that I am speaking about. And we'll look into in details regarding this in the fourth topic of the same module. Yeah, I hope in this session all of you are clear with. We started off with the optical generation and then we tried to find out alternative solution. What was the alternative solution? Is to have a source of hole injection, and that source of hole injection is turned out to be the P plus N region, and making the N region to be common between this forward bias junction and reverse bias junction, we formed a BJT which is referred as P plus N region. We understood the constructional details for the same, and also we looked into the different current components that can flow in the given BJT. What is a BJT that we considered? It is PNP region. Which is the other kind of BJT that I can have? It is NPN. Now, this working principle, it is the exercise for you to understand the working principle of NPN. All the currents that I can see in the P plus NP is just opposite to that of NPN. All the whole currents have to be replaced with the electron movement. So all these have to be totally inverse. That is what you have to look into. Here, if this is the emitter region that I am referring to, then this has to be heavily doped, this has to be lightly doped, collector and base, and this P width have to be made as small as possible. And this working principle is as assignment for you to understand and try to decode how this NPN transistor basically works. Yeah, so I hope all of you are clear with these topics. And then few more things that I have to consider here is, this is IE, IC and IB, which you know, which relates to the emitter current, collector current and the base current. Now what about this IEP relates to is, this is the emitter current which is contributing because of the holes that is getting moved or getting injected from the P plus region to that of the N region. Therefore I am representing as IEP. Done. Now see, this arrow I have made it little wider, whereas this arrow I have made it little small. See, all these are very minute things that you need to understand. Why am I making this arrow very small? Is that because whatever the electrons that we have in the N type will also tend to move to the P plus. So if the electrons are moving from N to P plus, what happens to the conventional current? You know, it is reverse direction. Therefore I have represented the conventional current in this direction, which contributes for the emitter current. Both the electrons which is getting diffused and the holes which is getting diffused, both of these contributes for the current flow. We have already seen in the second module, and that current is what I am trying to refer. Since we have P plus region, more number of holes are there, therefore the arrow width is widened, whereas here since it is narrowed down, less number of electrons are there which can diffuse into the P plus. As a result, I have reduced the size of the arrow. And both of these holes and electrons will try to contribute for what? The emitter current. That's why I've referred it as in this way. Yeah. So this is N, which indicates the electrons and the holes. Both of them contributes for the emitter current. Now comes the collector current, which I'm representing because of the holes which was injected into the N, which is trying to move into the P, and that is what I am trying to represent here. Now tell me, this arrow have to be wider, this arrow have to be smaller, and this arrow have to be little less than that of this size, because all the holes which is present in the P plus cannot move successfully into the P, because we know there is certain recombination that takes place which is represented as factor number 1. Therefore this size have to be little reduced when compared to that of this arrow. Done. Now we have to be very much careful with the widths of the arrows that you are using in this particular diagram. Yeah, I hope all of you are clear with this. Yeah, thank you one and all. We'll continue related to the amplification of BJTs in the next class. Thank you.